Picture a station platform in Devon, England in the summer of 1847. A train approaches at 40 miles per hour. Passengers glance toward the front, expecting the familiar sight of a smoke-belching locomotive, the roar of a firebox, the shriek of a whistle. They see nothing. No engine. No chimney. No driver stoking coal. The carriages simply glide toward them in near silence, propelled by a force they cannot see and can scarcely believe. This was the atmospheric railway, one of the strangest experiments in the history of transport. In an age defined by iron, steam, and fire, a handful of engineers proposed something radical, that trains could be moved by nothing more than the weight of the air itself. Between the rails ran a continuous iron pipe, perhaps 15 inches across. Stationary steam engines, housed in ornate buildings miles apart, pumped the air out of that pipe. Ahead of the train, a vacuum. Behind it, the full pressure of the atmosphere, 14 pounds pressing on every square inch. That pressure did the work locomotives had always done. The promise was intoxicating. No heavy engine to haul its own weight-up gradients. No sparks to set fields ablaze. No soot to choke passengers. An atmospheric train could climb steeper hills, accelerate faster, and run quieter than anything on conventional rails. Investors poured in fortunes. Newspapers called it the railway of the future. For a brief window between 1838 and 1848, some of the greatest engineering minds in Britain and Ireland believed the locomotive itself was obsolete, a crude relic already destined for the scrapyard. And yet today, almost no one remembers this technology existed. There are no atmospheric railways running anywhere in the world. The pipes were torn up, the engine houses left to crumble, the patents forgotten. Something went catastrophically wrong, something so simple, so small, that it undid millions of pounds of investment and the reputations of legendary men. To understand how a train could move without an engine, and why that miracle collapsed, we must begin not with iron or steam, but with something invisible and immensely powerful, the ocean of air pressing down on all of us. We do not feel it, but we live at the bottom of an ocean. The atmosphere above us stretches roughly 60 miles into space, and its weight presses down on every surface at sea level with a force of about 14.7 pounds per square inch. On a single square foot, that amounts to more than 2,000 pounds. On the flat side of an ordinary railway piston, the numbers become extraordinary. This was the force the atmospheric railway sought to harness. The principle had been understood for 2 centuries. In 1643, the Italian physicist Evangelista Torricelli filled a glass tube with mercury, inverted it, and watched the column settle. The empty space above it was a vacuum, and the height of the mercury measured the air's weight. A decade later, the German engineer Otto von Guericke staged one of history's great spectacles at Magdeburg. He joined 2 copper hemispheres, pumped out the air, and harnessed teams of horses to each side. 16 horses, straining in opposite directions, could not pull the spheres apart. Nothing held them but the pressure of the atmosphere. That demonstration lodged a powerful idea in the engineering imagination. If a vacuum could resist 16 horses, it could surely be made to do work. Thomas Newcomen used exactly this principle in 1712, building an engine where atmospheric pressure drove a piston down into a cylinder where steam had been condensed. The whole early history of steam power was, in truth, the history of the vacuum. The leap to railways was audacious but logical. Instead of a short cylinder, imagine a pipe running for miles between the rails. Pump out the air ahead, and atmospheric pressure would push anything sealing that pipe forward, mile after mile, dragging a train behind it. On paper, it was elegant, silent, and clean. The theory promised a railway free of the locomotive's dead weight, but a theory is not a machine. Someone had to build a pipe dozens of miles long, keep it airtight against the atmosphere, and let a train pass through its wall without breaking the seal. 2 men believed they had solved that impossible puzzle. The 2 men were Samuel Clegg and Jacob Samuda, working alongside Jacob's brother Joseph. Clegg was a gas engineer, a pupil of the great gaslighting pioneer William Murdoch, and he understood pipes, valves, and the sealing of vapors better than almost anyone alive. The Samudas were shipbuilders from London, practical marine engineers who knew how to make machinery survive punishment. Together they formed one of the more remarkable partnerships of the industrial age. In 1838 they secured their patent for the atmospheric railway system. Its genius lay in solving the central problem. How could a train be connected to a piston sealed inside a pipe, when the piston needed to slide freely along miles of track while the pipe itself stayed airtight? Their answer was a long slot cut along the top of the pipe, sealed by a continuous flap of leather. An arm reached down from the carriage, through the slot, to the piston inside. As the train advanced, the arm pushed the leather flap open just ahead of it, then pressed it closed again behind. A clever assembly of rollers lifted the seal, allowed the connecting bracket to pass, and resealed the pipe in a single motion. To prove it worked, the partners built a demonstration line at Wormwood Scrubs, west of London, in 1840. Half a mile of pipe, a stationary pumping engine, and a train that ran without any locomotive aboard. Curious engineers, investors, and members of Parliament came to watch. They saw carriages accelerate smoothly, run in near silence, and climb a gradient that would have taxed a conventional engine. The demonstration was a sensation. Reports praised the smooth motion, the absence of smoke, the eerie quiet. Here at last was proof that the theory could be made real. Samuda published pamphlets brimming with confidence, projecting speeds and efficiencies that outstrip steam. Railway companies, locked in a frenzy of expansion, began to take serious notice. But a half-mile trial in the flat outskirts of London was one thing. To convince the world, the atmospheric system needed a real line, carrying real passengers, over real hills, day after day, in every kind of weather. To understand both the triumph and the tragedy, we must look closely at the machinery hidden between the rails. At the heart of the system lay the traction pipe, a continuous iron tube laid down the center of the track. On the South Devon line it measured 15 inches in diameter, on lighter lines less. Inside ran the piston, a snug disc of iron and leather that filled the pipe completely. When the stationary engine pumped air out ahead of it, the atmosphere behind pushed the piston forward with enormous force. The piston connected to the train through a bracket that rose out of the pipe and fastened to the leading carriage. But the pipe could not simply be open along the top, or the vacuum would vanish instantly. This was where the continuous longitudinal valve came in, running the entire length of the line. The valve was a strip of leather, reinforced and weatherproofed, hinged along one edge of the slot and sealing against a fixed iron surface on the other. Ahead of the train, the leather lay flat and airtight, holding the vacuum. As the carriage approached, a set of rollers mounted beneath it lifted the flap open, just enough for the connecting arm to pass through. Immediately behind, another mechanism pressed the leather back down. To make the seal airtight against 14 pounds of pressure, the flap was coated with a compound of tallow and wax, and in some designs a second iron weather cover shielded it from rain. When everything worked, the effect was miraculous. The train slid forward with no engine, no smoke, no noise but the rush of air and the soft whisper of rollers on leather. Gradients that would have defeated a locomotive were climbed with ease. Acceleration was smooth and strong. But look at what the system demanded. Every foot of leather along miles of track had to open and reseal thousands of times, in heat and frost and rain, without ever failing. A single leak would let the atmosphere flood back, and the vacuum and the train's power would collapse. Everything depended on the leather, and to test whether leather could truly withstand the years, the atmospheric railway needed its first true trial by weather on a steep coastal line in Ireland. That trial came at Dalkey, on the rocky coast just south of Dublin. In 1844, the Dublin and Kingstown Railway extended a branch up a steep, curving incline to the granite quarries at Dalkey, a distance of about 1¾ miles. The gradient was punishing, rising roughly 1 foot in every 100 and tightly curved, exactly the kind of terrain where a conventional locomotive struggled to keep its footing. It was the perfect place to prove the atmospheric system. A stationary steam engine of 110 horsepower was installed at the top of the incline, at Dalkey. Its job was to pump the air out of the 15-inch pipe laid up the track. When the vacuum was drawn, the piston beneath the train was pushed upward by atmospheric pressure, hauling the carriages from the harbor at Kingstown to the quarry summit without any engine aboard. On the return journey, the train simply coasted back down under gravity, controlled by its brakemen. The results astonished observers. The atmospheric train climbed the incline smoothly and silently, reaching speeds of 30 to 40 miles per hour, and on one celebrated run, when the vacuum was especially strong and the train especially light, it was clocked at over 60. No locomotive of the day could match that on such a gradient. Passengers marveled at the absence of smoke and sparks, the gentle acceleration, the strange quiet. The Dalkey line ran successfully for years, carrying thousands of passengers up and down the coast. It became a place of pilgrimage for engineers from across Europe, who traveled to see the impossible made ordinary. Here was working proof, day after day, that a railway could run on air. Among those who studied Dalkey closely was the most celebrated engineer in Britain, a man of boundless ambition and spectacular achievement, already famous for his bridges, his tunnels, and his broad-gauge Great Western Railway. He watched the atmospheric trains climb the Irish hillside and saw not a modest branch line, but the future of an entire railway network. Isambard Kingdom Brunel was about to stake his reputation and millions of pounds on the weight of the air. In 1844, Isambard Kingdom Brunel traveled to Dalkey and watched the atmospheric carriages climb without smoke or fire. He came away convinced. Brunel was already the most celebrated engineer in Britain, the man behind the Great Western Railway, the Thames Tunnel, and the steamship Great Western. Now he staked his reputation on air. For the South Devon Railway, running the difficult coastal line from Exeter toward Plymouth, Brunel rejected conventional locomotives entirely. The terrain was steep, with gradients as sharp as 1 in 37 near Dainton and Rattery. Atmospheric traction, silent and powerful, promised to conquer those slopes without the weight and slipping wheels of a steam engine. The directors approved a budget that would swell past £400,000, an enormous sum for the 1840s. Along the route, Brunel raised a chain of magnificent engine houses, one roughly every 3 miles, at Exeter, Countess Ware, Turf, Starcross, Dawlish, Teignmouth, and Newton. Each was a cathedral of industry, built in an ornate Italianate style, with tall square chimneys, disguised as campaniles. Inside stood massive stationary steam engines, some rated at 82 horsepower, driving air pumps that would draw the vacuum from a 15-inch iron traction pipe laid between the rails. The pipe stretched for miles, sealed along its top by a continuous leather flap. When the pumps ran, atmospheric pressure of nearly 15 pounds per square inch pressed against a piston beneath each train, hauling the carriages forward. On September 13, 1847, the first atmospheric trains carried passengers from Exeter to Teignmouth. For a time, it worked. Trains reached 68 miles per hour on trial runs, gliding up gradients that would have defeated the locomotives of the age. Passengers marveled at the smoothness, the absence of cinders, the quiet rush of speed. Brunel had built the largest atmospheric system ever attempted, 20 miles of vacuum-driven railway threading the Devon coast. The engineering press hailed it. Investors watched their shares. The confidence seemed vindicated, the multi-million-pound bet on the edge of triumph. But the entire system depended on one fragile component, a strip of oiled leather exposed to weather, wear, and hunger. That strip would soon begin to fail. The leather valve was the heart of the machine and its fatal weakness. Running the full length of the pipe, the flap had to lift as the piston carriage passed. then seal shut again behind it so the vacuum could hold. To keep it airtight, the leather was treated with a mixture of tallow and other oils. In the summer heat, the oils dried out. The leather cracked and stiffened, and air leaked into the pipe. In winter, the same leather froze solid, sometimes shattering when the piston forced it open. Salt spray from the Devon coast attacked the material relentlessly. Rain washed away the sealing compound. Every problem meant the same result. The vacuum leaked, the pumps worked harder, and the coal bills climbed. Maintenance crews walked the line constantly, re-oiling and replacing sections of leather by hand. And then came the story that has haunted the project ever since. The tallow and fish oil dressing, some accounts insist, attracted rats. The vermin gnawed the leather flap, chewing holes in the very seal that held the atmosphere at bay. Whether rats truly feasted on the valve, or whether the tale grew in the telling, the leather was undeniably rotting. Iron fixings corroded. The tannin in the leather reacted with the iron plate beneath it, weakening both. Sections had to be renewed far faster than anyone had budgeted. The engines, meant to pump for a few minutes per train, ran almost continuously to compensate for the leaks. Coal consumption soared. The 400,000 pounds spent on engine houses and pipe now demanded a river of further spending simply to stand still. Passengers still enjoyed the smooth ride, but behind the scenes the accounts told a grimmer story. The atmospheric railway was consuming money faster than it earned it. Brunel, who had promised silent efficiency, faced mounting reports of failure along every mile. The shareholders grew restless. The elegant Italianate engine houses, once symbols of the future, began to look like monuments to a mistake. The vacuum could not hold, and with each leak, the pressure mounted toward a decision no engineer wanted to make. By the summer of 1848, the numbers were undeniable. The South Devon Railway was paying enormous sums to keep the leather valve functioning, and still the train stalled when the vacuum failed. Running costs on the atmospheric section reached roughly 3 shillings per mile, compared with less than 1 shilling for conventional steam. The promised savings had inverted into ruinous expense. In August 1848, Brunel presented his report to the directors. The verdict was blunt. The atmospheric system should be abandoned. The great engineer, who had championed the technology and staked his name upon it, recommended tearing out the very apparatus he had built. On September 9, 1848, atmospheric operations ceased. It had carried passengers for barely a year. The line reverted to steam locomotives, the technology Brunel had tried to leapfrog. The losses were staggering. Estimates placed the wasted investment near 400,000 pounds, much of it sunk into the pipe, the pumps, and the ornate engine houses now rendered useless. Brunel waived his fee, a rare acknowledgement of failure from a man not given to admitting error. The engine houses fell silent. Some were demolished, their machinery sold for scrap. The iron traction pipe, thousands of tons of it, was lifted and sold at a fraction of its cost. What had been the boldest transport experiment of the age became a cautionary tale told in engineering lectures for generations. Meanwhile, the rival technology was surging ahead. Steam locomotives were improving at astonishing speed. More powerful boilers, better valve gear, and stronger frames meant they could now climb gradients once thought impossible for adhesion alone. They needed no continuous seal, no chain of pumping stations, no strip of vulnerable leather stretched across the countryside. A locomotive carried its own power wherever it went, independent and self-contained. The atmospheric dream, silent and elegant, simply could not compete with a machine that never leaked. The future of the railway was decided not in the laboratory, but in the ledgers of the South Devon line. Steam had won. Yet the idea of moving trains by air would not entirely die. It lingered, buried in the pipe, waiting. Today, fragments of the atmospheric railway still stand along the Devon coast. The pumping station at Starcross survives, its tall Italianate tower rising beside the estuary, now a small museum to a vanished ambition. Sections of the original iron traction pipe are preserved in collections, their leather-lined slots, a silent record of the engineering that almost was. Trains still run the South Devon line Brunel built, hugging the sea wall at Dawlish, but they are hauled by diesel and electric power, not by the vacuum he imagined. The atmospheric railway was not simply a folly. Its core principle was sound. Air pressure genuinely could move trains smoothly and powerfully, up gradients that defeated the locomotives of 1847. The physics never failed. What failed was a material, a strip of oiled leather asked to do something no leather could sustain, to open and reseal, mile after mile, day after day, through frost and salt and heat, without leaking. And so the idea refused to die entirely. It kept returning, reborn in new forms. The pneumatic tube systems that carried mail and parcels beneath cities in the 19th century used the same principle. The beach pneumatic transit briefly moved passengers under New York in 1870. In the 20th century, atmospheric trains reappeared in Brazil, where the air removal system still runs on compressed air, propelling vehicles by pressure against a plate inside a channel. Modern Hyperloop proposals, promising near vacuum tubes and frictionless speed, are in a sense the atmospheric railway's distant descendants, chasing the same dream of trains moved by the pressure and absence of air. Each generation rediscovers the elegance of the vacuum. Each must solve the problem that broke Brunel: how to seal a moving system perfectly, forever, at reasonable cost. The seal is always the challenge. The engineering that stops the leak is always the deciding factor between triumph and abandonment. The story of the atmospheric railway endures because it captures a truth larger than one Victorian line. A brilliant idea can be undone by a single, humble component. The vacuum was faultless, the vision was sound, but the whole enterprise rested on a strip of leather, and that strip could not hold. Air could move trains, leather could not.